Okay, and this is the slightly more detailed run through of RTran and especially what you need to do in the input file to set up a simulation. So RTran is a strategic transport simulation model, and it's kind of like it's basically a traditional 4-step travel demand transport model, more or less. But I've simplified in some areas. I've kept everything I think is essential to having a realistic transport simulation, but I have tried to make it simpler to basically to specify all the inputs. So you'll see that as we go along that there's been some decisions made just to make it easier for teaching purposes or for just general calibration purposes. Also the run time's a lot faster than what you would get in a lot of the modern strategic travel models. So I'll double click on the RTran folder. You should have run through all the previous videos that tell you how to set up RTran. So I'm not going to run RTran now. I'm going to concentrate more in this video on the input file to RTran, which in stepping through it should give you a better idea about what RTran is and some of the decisions made for the simulation. So if you open up the input file, you'll get a spreadsheet, and I might come back to this first sheet. So this first sheet is called core inputs, and we specify some of the core inputs for the simulations, and the value of time for travellers and things like that. And I'll come back to that because each one of these takes a little bit of time, and I might go through the ones that have a bit more of a visual or a spatial interpretation first, because they're probably easier to start with. Okay, so in a 4-step travel model, you have trip generation and trip attraction. So in this sheet, we're specifying the trip generation for our city, for the region being simulated. So just to remind you again, for this particular city, there's 400 zones, 20x, 20y, I think it's 400 zones. And this sheet, the trip sheet that I've clicked on, specifies the total number of trips from each zone. And that's just something that you specify. So you would actually want to have a trip generation model separately generate this, or if you're just mucking around, you can put in the numbers yourself by hand. But if you're running sort of a realistic simulation for an actual city, you'd obviously want separate to RTran. You'd want to have a trip generation model, and that's external to the model. So there's no trip generation estimated within RTran. You just specify it in this spreadsheet. This spreadsheet, you could feed that from a separate model, but I'm just going to assume that you've done that, or you've done whatever you need to do, and now all to generate trips, or to determine which zones generate trips, and now you can just enter it in this sheet. So you just click on any cell and you enter. In this case, I've entered 1,526, and that's how many trips are going from that individual cell. Now, just to point out, RTran simulates all trips as return trips. So if you want to think about these cells as suburbs or something like that, so out here is out towards the edge of the city, and that's mostly going to be sort of suburban living in most cities, and they're going to travel. It's going to be trips from this cell to other areas, when people go to work or whatever, and then a trip back. And in RTran, all trips are of that kind. All trips are return trips. So if in this case, there's 1,266 trips from this particular cell, this zone, and they will all be return trips. So there'll also be 1,266 trips returning back to this cell. And in the simulation, they're called two separate legs, so they're modelled separately. So for example, if you were modelling peak traffic only, you'd have first leg, which would be the AM peak, and that would model all the trips in the AM, basically people going to work and other non-work trips, but people going to work, and then the return trip back, the second leg, is the return end of all those trips. Okay, so we don't model tours or multi-leg trips or anything like that in our trains. That's one of the simplifications that's been made. Okay, so you see here in this particular city, I've got a sort of traditional suburban sort of city, so most of there's more trips in the more heavily populated, the denser suburbs, but right in the middle it falls off a bit, and that's because in here I'm assuming that there's going to be a lot of jobs in the centre CBD, and actually fewer actual households living there, so there's fewer trips generated to those, there's fewer trips generated from these inner city squares in the morning peak. So I'm going to talk in the simulation as if we were simulating the commute, morning peak and evening peak to and from. So you don't have to just simulate that, you can simulate other periods, but just to make it easier to explain, that's sort of how I'm going to talk. So for that reason, I've set up the inner city to not generate too many trips from each of these squares, because it's mostly jobs and offices and things like that. So these inner city squares are going to be trip attractors rather than trip generators. Okay, so that's hopefully gives you an idea about what the trip sheet is for, and as I said, you can modify that any way you like if you wanted to have a different sort of city. You change the number of zones as well, that's fine if you want to make a larger or smaller city, but the basic setup of each of these spatial spreadsheets is the first row must be, the first row is ignored, so you can put really whatever you like in the first row. And then from then on, all the other rows have to have the same length, so you can't have sort of a jagged city that has to be rectangular. And then you specify as many of those as you like, and when you're finished, you just signal that you're finished by having a blank row. So you see row 22 here is blank, it has no numbers, and that's just what tells RTran that you're happy with your city and you don't want to specify any more information in this particular sheet. Underneath that, I've just whacked in a row telling me what the x coordinate is. That's just my own reference, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, so I can quickly look at this square here is x coordinate 10, y coordinate 10, and that's just to help me keep track of the squares. And then usually in each of these sheets I've tried to put a really brief description of what the sheet shows. So this one, it shows the total number of trips from each zone during the modelled period. And for this explanation, I'm just going to think about the modelled period as the commuting, which is both the AM to trip and the PM from trip. There's some, and so hopefully that's enough for the trips. So that's trips from, trip generation. The activity sheet is trip attraction. So that's the opposite. These numbers in each of these zones specifies how attractive that zone is. So basically, I won't talk about the mathematics involved, not in this video, because I'm just trying to give a quick run through, but the higher the number, the more trips there will be to that zone. So it's not exactly the case that these numbers specify the number of trips to. So it's just because I put 1,485 in that zone, it doesn't mean that there's 1,485 trips to that zone. What it does mean is that this zone, the number of trips to this zone will be proportional to this number. So you see this is 1,485, this one's 140. What that means is there will be 10 times the number of trips to this zone here than there will be this one. Actually 10 and a bit, but you get the idea. So the absolute numbers in the activity sheet doesn't matter. It's just the relative numbers that tell you how many trips are going to be to each zone relative to the others. Because the total number of trips, remember, if we go back to the trip sheet, the total number of trips is specified here. So we know the total number of return trips that are going to be made. The activity sheet is just going to be to help us work out where those trips go to. And the trips to each zone is proportional to the numbers in the activity sheet here. Okay, so hopefully that's pretty self-explanatory. So we know where trips are generated from. We know where they're attracted to. And then we need to specify a number of other sheets which give us some information about the city. This car speeds one talks about, well, basically it's just specifying the speed in kilometres per hour in each zone by car. This is the uncongested speed. So here I've got a really boring city. It's 40 kilometres an hour in every zone. And I should mention the road network assumed in this particular simulation. You can change it to be something different, but in this simulation the road network's just a straight grid. So in this square here that I've clicked on, that's assumed to be linked to the square immediately above it, the square immediately below it, and the squares either side. So it's a straight grid. So if you're in here and you're travelling to this square, there's a link between those two squares. So the links are kind of implied and they're just a straight grid. So here, as I said, I've got a really boring city. It's just uniform speeds across the whole city. Now let's go to the public transport sheets now. So the road network in this particular example is really easy. Very simple. Okay, the public transport one's a little more involved. So you see in the next sheet that I've got, actually the next two sheets, I've got one called bus NS frequency and one called bus EW frequency. It's actually, you can have as many of these sheets as you like. So any sheet that starts with the word bus and ends with the word frequency has information about bus routes in your city. In between that is just an identifier that you can use to sort of keep track of which bus routes you've specified in that sheet. You can specify them all in one sheet if you like, but sometimes it gets a bit busy then in the sheet. So in this, that's what you're allowed to specify in more than one sheet. So it's probably easier if I just go in a little more detail and you see by example what I mean. So I've called this sheet bus NS frequency. The bus and the frequency part is just fixed. You've got to have that at the start and the end, just so that RTran knows that it's a bus route information. In between, I've called the identifier for the sheets NS, just because these are all the north-south bus routes in my city. So you can see here, this is one bus route that I specified. Now you specify a bus route in a particular square by giving it a name, basically putting the name of the bus route in that square. You can call the bus route whatever you like. The only constraint is that you have to start. You have to call it something starting with a letter. So you can't call the bus route by number. So you can't have the 199 bus. You have to call it B199 or something like that. So here I've called my bus route along this particular route NS2 for north-south 2, because it goes at x equals 2. And all of the squares have to be contiguous. So for example, I couldn't delete this square here and have two NS2 bus routes, or Well, you could, but it doesn't really make sense to. That basically that'd be splitting into two separate bus routes. So here, NS2 is a north-south route. It runs right from the end of the city to the other end, and all the routes that you specify are assumed to be bi-directional. So there's buses that's going north to south, and there's buses going south to north. So this specifies the route that the bus goes on, but the frequency is also obviously an important bit of information, and you have to specify the frequency in at least one of the squares that the bus route is defined in. So here I've just done it up the top here, and you see the frequency is a 6, and that frequency is buses per hour. So there's 6 buses per hour of this bus route. And I don't need to specify it anywhere else because the frequency is the same over the whole route, obviously. You can, if you want to, have a frequency in each square, so you can type NS2 space 6 in all the squares, but you don't need to. You just need to specify in at least one of the squares along the route what the frequency is. Okay, and the rest are pretty obvious. Just different bus routes running north-south. So there's the north-south 4 route, there's the north-south 6 route, north-south 8 route, and you'll notice that the frequency, I've made the frequencies change a bit. So the north-south 8 route, because it runs sort of through this closer to the CBD, and the north-south 10 route, because it runs actually through the CBD, I've made the frequency faster. So the north-south 10 route actually runs 15 times an hour, so very frequent. Whereas the ones on the outer are actually still pretty frequent, but not as frequent as the central one. Okay, so that's my north-south bus routes. And then, predictably, I've got the east-west bus routes. Sorry, just to go back a second. You notice that the north-south bus routes, they don't go in every cell, every sort of column rather. So we don't have a north-south bus route going along here at x equals 5. And that doesn't have to be the case. You could have as many bus routes as you like if you wanted to have a really saturated bus coverage across your city. But in this case I've just left this blank, so I'm assuming that some areas aren't served by bus very well. And if we, I should just mention now, and I'll go back to the trip sheet because it's nicer to look at. Each one of these cells is, as I said, a suburb or a zone, but to give you some idea of the scale involved, each square is, even though it's not square, here, each one of these cells is actually assumed to be square in physical terms, and the size of the square is what you specify in the front sheet in this parameter. Grid square each kilometres, and in this case it's 1.5 kilometres. So that means all of these other cells, this zone here, is 1.5 kilometres by 1.5 kilometres. And so from that you can deduce that our city is 30 kilometres by 30 kilometres. So it's 900 square kilometres that we're modelling, and each one of these is 1.5 kilometres. So with that information in mind, and we go back to the bus frequencies, if you are unlucky enough to live in this particular cell, you don't have a bus route, a north-south bus route anyway. And so if you wanted to go north or south, you would actually have to walk to the NS2 bus or to the NS4 bus, and that walk would be a 1.5 kilometre walk. So you can do it, but it's not particularly short. And that will make a difference to how many people here catch the bus, because that's a bit of an impediment to catching a bus if you have to walk that far. And we'll see that in the results when we run the simulation. Okay, so bus north-south, bus east-west. Again, same as the north-south, you've got to specify the frequency somewhere. So here we've got the east-west 12 bus runs at 15 services an hour, as does the east-west 10 bus. So pretty frequent towards the centre of the city, and less frequent out towards the edges. Okay, so buses share the road network with the cars. They all travel at the same speed as the cars, and if we model congestion, which I'm not going to talk about in this video at all, the buses will slow down due to congestion the same way the cars will. So the buses share the road network with cars. They travel at the same speed as cars. So in uncongested conditions, for this city, the speed's always 40 kilometres an hour. Buses will travel at that speed, 40 kilometres an hour. But if there's congestion, they'll slow down just as cars will. And that's what allows us to work out how long a bus will take to get somewhere. There's one additional issue with buses, in that obviously buses have to stop, so really they do travel slower than cars. And that's reflected in the front sheet under the bus stopping time per square seconds. So in each square, in this case it's the 1.5 kilometre zone, we assume a bus stops for 90 seconds. That's to drop off and pick up passengers. So in reality, this will mean that buses are slower than cars, even though they use the same network. Okay. We've got our bus network. Trains are different, of course. They don't go along roads. So trains have to be specified separately. And again, trains are a little bit different from buses because you have to have 2 sheets for each set of trains that you specify. So again, you can use as many sheets as you like to specify the different train lines. But let's say you have 3 different train lines and you want to specify them in 3 different sheets. You've actually got to have 6 sheets to do that, because for each train line you've got to specify a frequency and you've got to specify a speed. So in this particular example, I've got 1 train line. So that means I've got 2 sheets to specify the frequency and the speeds, but you can have as many of those pairs of sheets as you like if you want to have more train lines. You can also specify more than 1 train line in the same sheet, but that's in this case I haven't done that. So the same way that we had the multiple bus routes in a sheet, lots of north-south bus routes going along here, you can do the same thing with a train line, and they can overlap. So you could have a train line that comes along here and went through the CBD up north, that's fine. Okay? Same as the bus route, you've got to give the train line a name, and that name has to start with a letter, can't be a number. So in this case I've given a really boring name. The train's called Mainline, and you see again somewhere at some point along the route that the train goes, you have got to specify frequency. So this is a very frequent train service. So we don't have a very extensive train network, but we do have 1 line that runs a high frequency, 10 services an hour. Now you specify the speeds for what rail travels along, and these are again in kilometres per hour. So you see the mainline train runs at 60 kilometres an hour, and that's obviously not affected by congestion. So if there's congestion on the road network and road speeds slow down, the speed of the train isn't affected. This is separate to the road network. So that's why if you had a dedicated busway, let's say, with dedicated bus space, you would actually model that in RTran as a train. So you'd have to call the bus service a train if it was unaffected by congestion along its route. Anyway, so I won't go into that, but 1 train line, 60 kilometres an hour. Obviously, a train also has to stop to pick up passengers, and so in the front sheet, the core inputs sheet, this is where you specify the number of seconds that a train stops per square to drop off and pick up passengers. And it's less than the bus here because I'm assuming train stations are spaced further apart than bus services. I'll come back to that in more detail later. Okay, so that's the train service. Next sheet is PT waiting time wait, which sounds a bit odd. PT stands for public transport, so this is the public transport waiting time wait. So basically, when RTran runs, it will allow people to hop off some services and hop onto other public transport services. So for example, someone could get on the NS bus 4 here, travel to here, basically travel to x equals 4, y equals 10, and get off the bus at this square, and then hop on the east-west 10 and catch that into the city. So that means at this particular square, square 4, x equals 4, y equals 10, they have to get off and wait for the east-west service. People don't like waiting. All the research shows that people don't like waiting, and they value that time as really unproductive. And so you have to account for that by saying how unpleasant people find waiting time. And here I've used pretty much the standard sort of number that you'd use in any transport simulator, and that's 2. So that means if you would have to wait 5 minutes for a transfer, or when you transfer you had to wait 5 minutes, that actually is perceived or counted by the person as 10 minutes because you have to multiply it by 2. So that's the factor here. So 4, 10. And you see here I've used the same factor here for the whole city. So no matter where you transfer, people don't like transferring, so you double the actual waiting time to get the perceived waiting time, just to reflect the fact that people don't like that. Might just pause that there and come back in a second video.